Alrighty, today we're following up on our conversation about drainage by getting down into some of the nuts and bolts. We're going to talk about how do we align drainage tile in a field, particularly pattern drainage. How do we use field topography to get the best performance of that system? How do we determine appropriate depth and spacing, and using some expert guidelines? And then finally, how do we calculate the necessary pipe diameter for laterals and for mains in order to accomplish the recommended amount of drainage in our situation? So remember, we talked about different drainage layouts. We talked about the gridiron layout here, where you have these guys, these smaller lines here, the laterals, and then a single main line here. We might also have something called a double main. That's this one down below, where maybe we've got maybe this is a waterway, could be a grass waterway even. Sometimes we use this kind of construction to keep saturated conditions out of a grass waterway when we're trying to get that grass to establish, and we want those conditions to be dry enough for the grass to get good coverage. We might put a drainage system like this in the field, if we're doing drainage in the field anyway, to route those mains alongside the grass waterway to prevent saturated conditions in that waterway. There's also the herringbone style. And remember, this is going to be appropriate when we've got kind of a channel or a draw area here, not necessarily such a place of concentrated flow that we would want to put a grass waterway in, but maybe we've got two sides of the field that kind of come together. We'll put a main line down the middle and then put laterals kind of up the hill slopes a little bit more. And then this one that is sometimes called the random, but really is more like a strategic layout, where we're really only draining selective parts of the field that most need it. And within each one of those sub areas, we may have something that looks like a herringbone design or a gridiron design, or we may just have slightly more random looking arrangement of the tile lines. This is the kind of thing that we would use for like pothole areas, surface depressions that may have extra neat, maybe they have really tight, dense soils in there that are poorly drained. We just want to give them a little bit of help by draining just strategically in that area. But if we're draining the whole field, we're probably going to be using something like a gridiron or a herringbone. So I better stop my phone from dinging at us. Hold on. Okay, so now one question that arises when we are doing a gridiron design in particular is, which way do we orient the laterals versus the main with respect to field topography? So the guidance is that it's the most effective when you can put the laterals sort of along the contours of the field, as opposed to running them straight up and down the hill. And the reason for that is that if you remember that surface flow, and to a large degree subsurface flow, goes downhill perpendicular to the contours. And if you align the laterals so that they are also kind of parallel to the contours so that the water is flowing across them, you are helping the water to enter into those tile lines. Whereas if you put them so that they are going in the downhill direction, you're going to get a lot of movement of water that kind of runs in between the tile lines and doesn't necessarily run into the tile lines. That's not entirely true, because you're also going to get kind of helped along by the moisture gradient in the field, that if the water senses an outlet where the tile lines are, it's going to be drawn in that direction. But it's not going to be as effective as if gravity is also helping to pull that water into the tile line. So it's desirable if you can place the laterals parallel to the field contours as much as possible. Now, in any given field, you're going to have slopes in different directions. And so we also often have subsections of the drainage system. We might not be tiling the entire field with the same gridiron layout, the whole thing, but rather we might have subsections that Here's one here, here's a subsection here, and then we're linking them all together. Another thing that we have to think about in layout, are there any special features that we need to drain with an additional element to the drainage system? So surface inlets, for instance, like we might find on the upslope side of a terrace if we're using a tile drain system to handle water that impounds behind there. I have a surface inlet right there. Or if we've got sort of a low area in the field that is poorly drained, doesn't have any natural surface drainage because it's a closed depression, meaning it's like bowl shaped and water doesn't flow out. Water will flow into it, but doesn't naturally flow out of it until the water level gets so high that it overflows. Those would be cases that we might want to have a surface inlet. So here's a couple of pictures of what these surface inlets look like. The most common are like this, just a pipe that sticks up out of the ground. It's got holes in it of some kind, and sometimes they're corrugated metal ones with holes, but a lot of times they're this hard plastic like this. But there's also people tinkering with different designs of these surface inlets. So here's an example of one known as a water quality inlet. And if it looks a little bit like a dense grass cover, that's kind of what it's meant to mimic. And the idea here is that in this old riser style with just the holes in it, if you've got, this is surface runoff that's here that you're trying to drain away, and it's probably going to have sediment particles in it. And if it's got sediment particles in it and we're in an ag situation, it's probably also got phosphorus adhered to those sediment particles. And if we'd rather not load up our subsurface drainage system with sediment and the phosphorus that goes with it, maybe we could have a system like this, which kind of filters out those sediments and adhered pollutants before that water enters the surface inlet, just by having this system that's more difficult for water to flow straight through. And if it can't flow straight through and it's got to wind around, then some of those sediment particles are going to get caught by this roughness before it enters the drain system. Okay, so then we have to think about other things that might affect the layout. So some other guidelines. So the primary guideline we already said is to attempt to orient the laterals so that they are perpendicular to the downhill flow direction. They follow the contour lines of the field. Other guidelines are, on a large installation, we'd want to have a minimum number of outlets, and the reason is because those are typically more expensive. They have to be a more robust, hardier material. You have to put an animal guard on them so that you don't get critters moving back up into the tile line and setting up residence there. If it's outletting into a drainage ditch, you might want to have a one-way valve on there so that you don't get backwater from the ditch flowing back up into your drainage system under high flow conditions, but instead it's a system that only lets water out but doesn't let water in. So all that stuff is going to add to the cost of the drainage system. Speaking of cost, it's more desirable to have a short main and long laterals. And again, the main is typically going to be a larger diameter because it's collecting water from all of the laterals, and the laterals are typically going to be a smaller diameter, and we'll see in a couple minutes why that is. We'll run the math on that. So just to save expense, you should drain the whole field. You'd rather do it with the less expensive tile line over more of the area. So there's a guideline there. You also want to take into account any natural waterways and concentrated flow path. Maybe use those as boundaries between subsections. So follow along those natural flow paths with the main or the submain. Particularly in areas where the topography is a little bit rumply, you're going to have to really take into consideration the depth of cut in different locations. That also comes into play if you are trying to drain a very flat area, but you have to put some slope on the tile line in order to get that water to flow through there. It could mean that if you're draining a large area with the same line, in order for you to put a little bit of slope on there, you're going to end up being shallow in depth at the top end and deep in depth at the bottom end. So you're going to have to kind of play with that to make sure that you're not putting any of that tile line super deep. I suppose I should have put this up above this other one. It's also a bad idea to have a tile line that actually crosses a waterway. So typically you would run a tile line maybe up to the waterway and then have a main or a submain that's along that line. Okay, so the next thing that we need to think about, so those are considerations for aligning the drainage with the topography. The next questions are about depth and spacing. How deep are we going to put these? So the depth would be, if here's the surface and here's the tile line and it's kind of facing us, and maybe here's its neighbor. These are two adjacent laterals. How deep does this need to be? So one of the things that we could consider is that we're really trying to get excess water out of the root zone here. And so we might want to put them at a depth that is below the typical rooting depth for the crops that we're trying to grow. So typically that would be 3 to 4 feet. But we also need to recognize that the water table between those drain lines at steady state conditions after all of the gravity drained water has left the system, the water table actually has this kind of humped nature where it's closer to the surface midway between two adjacent laterals. And so there's this relationship between like the depth at this midway point and the spacing. The closer you put those laterals together, the more of the field experiences an effective depth above the water table of 3 to 4 feet. The farther that they get apart because of that humped nature of the water table, more of the field is actually experiencing a depth to water table of like 1 to 2 feet. So you can't think of depth and spacing as totally independent. That they are in fact interrelated. And there's actually a whole bunch of math that relates depth and spacing and effective amount of drainage, but it's all calculus based, and most of the time people don't use it unless they are like a research engineer studying performance of subsurface drainage systems. More likely, people are using kind of local expertise and guidelines that are based on soil type to try to come up with a good depth and spacing. So this is an example from an extension publication at the University of Minnesota that breaks it down into major soil type classes, clay loam through other sandy loam, and looks at, okay, if you want sort of middling drainage, this 1/4 inch and 3/8 inch, and 1/2 inch is effectively, it's a drainage depth per day. That's actually a drainage like amount, volume per unit area per day. And we'll talk a little bit more about this in a sec. But you can see that maybe some different recommendations for depth and then different recommendations for spacing depending on how much drainage you want. So a clay loam, for instance, that drains very slowly, you're going to put that a little bit more shallow and a little bit closer together compared to a sandy loam that has pretty good drainage. You can put that a little bit deeper and a bit farther apart and still have the same amount of drainage effectiveness. But those are very general guidelines. You can also, in most states, you can also find more specific recommendations that don't just go by general soil type, but in fact go by soil series. So here's an excerpt from the Iowa Drainage Guide that gives drainage recommendations by soil series. Here they're all in alphabetical order. So for instance, this Amana soils, the natural soil drainage is somewhat poor. It also commonly experiences flooding, so the drainage guide will tell you might need to think about protecting that soil from flooding. And that at 36-inch depth, we're going to place them a little bit closer together. At 48-inch depth, we're going to place them maybe a little bit farther apart. Is that backwards from what I said earlier? It is. Okay, so, well, we'll think about that. I'll follow up later. There is a relationship between depth and spacing. So in Iowa and in most places that have a lot of drainage happening, you can find drainage guidelines on depth and spacing that are, well, certainly on spacing as a function of depth that's specific to the soil types that you're working on. Well, this doesn't necessarily tell you for any of these soils whether you should pick a 36 or a 48-inch depth. So some of this is going to have to deal with cost and the number of lines that you end up putting in. Next time, we're going to talk about the relationship between subsurface drainage and water quality, and we'll discuss the idea that shallower drainage drains less water out of the system. And so to the extent that drainage water takes with it nitrate that we might not want to be exporting, if we can reduce the total amount of drainage volume, we can also reduce the total amount of nitrate that's leaving the field. And so this would, if you're water quality minded, this would push you towards a shallower depth more than a deeper depth. And actually, shallow drainage as a concept is even shallower than that 36-inch depth. And then you got to tighten the spacing up even more. Okay, so use local guidelines for depth and spacing. And then we have to think about the capacity of the drain system, because how much water we need to move through there per unit time is going to tell us how big the tile lines have to be, so what diameter we need to have. So when we think of drainage capacity, we're really talking about a flow rate that those systems can accommodate. And just like when we were talking about runoff volume and peak flow rate, I'm using lowercase q for a flow rate here. This flow rate through a tile drain system is going to be a function of the drainage area and kind of a surface drainage velocity, like how fast are we draining water out of the system vertically? And we call that a drainage coefficient. The drainage coefficient, or DC, is a depth of water to be removed from the system and it's per unit time, but actually we're very specific about what that unit of time is. When we create tabulated drainage coefficients, we consider a 24-hour period. So we're going to find recommendations. I'm missing some letters in this word. For drainage coefficient that vary by soil type a little bit. We've only got 2 categories of soil type: a mineral soil and an organic soil. Organic soils are like those peat soils. You remember when we were talking about soil-water relationships, and we were showing the relationship between soil water content and soil suction pressure, and it was like kind of the sand, silt, clay soils had sort of a range of graphs, and then there was the peat soil and was doing something kind of like all by itself. That line was way out there. That would be an organic soil. The other ones whose soils are primarily mineral particle sizes, kind of doing more of a clustered thing, so we lump them all together for the purpose of drainage coefficient. The other thing that we're going to vary this drainage coefficient by, again, very loosely, just 2 different categories, is crop type. And it's going to be ones that are really sensitive to excess drainage or to excess water content. Oops. Using theta as a shorthand for soil moisture content. So usually in the tables, we break this into truck crops versus field crops. So truck crops are going to be like vegetables, and I think of it as things that you might find somebody selling off the back of a truck. Typically more sensitive to excess soil water content than a field crop, corn and soybeans, which are sensitive to excess soil water content. This is partly why we're doing drainage in the first place, but they can handle a 24-hour period of high water table without completely falling apart. The truck crops are a little bit more, a little bit less resilient to those short periods of high water content. So we're going to want to drain more out of the truck crop scenario than we do in the field crop scenario. And then the final thing is, do we have any surface connections? Are we also allowing water? Is the only way that water is getting into that tile line by coming through the soil, or do we also have direct surface connections to drain surface water as well? Because if we do, we're going to need to increase the capacity of the lines. So here are some examples of drainage coefficients for different scenarios. So in this table here, we've got without surface inlets. So this would be just tile lines buried under the ground, not connected to the surface. So we see that those field crops on a mineral soil, this is mostly where we are going to be working. We have 3/8 to 1/2 inch per day of drainage coefficient. And then those organic soils that will that have a lot higher capacity to take water in, we're going to have a higher drainage coefficient. And then if we've got truck crops that are more sensitive to high water content, we want to get water out of there faster, so we're going to have a higher drainage coefficient, allow for more drainage during a 24-hour period. And then if we look at the same information, but now we've got different types of surface inlets. And again, we've got these 2 categories, field crops versus truck crops, 2 different types of surface inlets. One is a blind inlet. This is more commonly called, and certainly in residential and more urban settings, is called a French drain. This is where you put the tile or the drainage line underneath like a gravel or sand bed that you we dig a trench for the tile line, and then you backfill not with soil but with a really high permeability material, and maybe put a kind of geotextile fabric over the top of it, and then a little bit of soil cover on top, but a connection directly to the tile drain by moving through that really highly porous material. The open inlets are like the risers and the standpipe, the surface inlets that I showed you a picture of a little bit earlier. So those open inlets that allow water directly into the tile drain from the surface, we're going to see that those, for the same circumstances, will allow a little bit more water in than routing water through the porous material, but the porous material will have a higher drainage capacity than when that material is entirely soil. Okay? And then, so what do we do with this information? I actually need another slide in here. Okay. So with this information, we can go back to this idea that the flow rate through the tile line is the drainage area times the drainage coefficient, and we might have to do some unit conversions there. And if we operate under the idea that these drainage systems are essentially open channels rather than pipe flow like you might have experienced in a fluid dynamics class, pipe flow being pressurized at one end or the other, sometimes both, these are open to the environment at both ends. So it's just natural flow that dictates how fast it moves. So the things that affect the flow rate, the capacity of those drainage lines are going to be the slope of the drainage line. The steeper the slope is, the faster that water can flow through there. The roughness of the material is going to play a role as well. And also what percentage of the flow is in contact with that rough surface. And when you put all those things together, those of you who have taken a fluids class, maybe towards the end of that class, you got into open channel flow and you were introduced to the Manning's equation. This is the same equation that we might use to design a grass waterway. It's how water flows in an open conduit. But if we apply that to the drainage situation, we end up with an equation that looks like this. You've got some crazy exponents here, but that's what it is. So where D is the tile diameter in inches, Q is the flow rate in CFS, so that's cubic feet per second. And you can see that if we got a drainage coefficient that's in inches per hour right off the bat, we need a little bit of unit conversion in order to use this equation. N is known as the Manning's roughness value. You can find estimated values of Manning's roughness for different types of tile material. It's unitless. And S in this equation is the slope of the tile and we want that to be in decimal rather than percent. Okay, so if we've selected the spacing, let's imagine, so we've got a system that looks like this. So here's the spacing between each of those. If we wanted to know the drainage area for each one of these laterals, it's like halfway to the next tile on either side. So it's essentially equal to however long those drainage lines are times the spacing. That's each of those laterals is draining that amount. The main line is going to be draining the whole field. That makes sense. And we'll do an example of this, but that's how we're going to get the area of the drainage system. So for the main, it's the whole area. For lateral, it's length times spacing. Slight adjustments there, but we'll see how that plays out when we do the example problem. Okay, and then we select the drainage coefficient based on what kind of soil type, what kind of crop, and what our surface drainage situation is. And then all that happens there is that we need to do unit conversions. and then this equation. And we're going to get inevitably some decimal answer. But in fact, we need to keep in mind that you can only buy tile corrugated plastic tubing in commercially available diameters. That's 3, 4, 5, 6, 8, 10, 12, 15, 18, and 24 inches. And so typically we're going to want to round up, unless we're super, super close. So if we ended up with a required tile diameter of 4.4, we're probably going to select a 5-inch diameter required. The consequences of selecting a smaller one that's required is that you're essentially simulating a smaller drainage coefficient. If you pulled from the large end of this range, maybe that consequence is not so terrible. If you were on the small side and then you round down, you are getting even less drainage than that. And so that's probably, unless you're in a really a situation where that difference makes or breaks the project in terms of cost, you're going to want to allow for more capacity as opposed to less. The other thing that happens is that over time there might be some degradation of the capacity if you've got the settlement of fine particles in the tile line. If you haven't designed the system for surface inlets and you are already on the small side of the capacity, your ability to add surface inlets and get any effect from those surface inlets is very small if you're already maxed out on capacity. So things to keep in mind when you're looking at this relationship between drainage coefficient and tile diameter. Speaking of being able to prevent a lot of buildup of material in there, I mentioned last time that there were recommendations for minimum slope in a tile line, depending on the material, in order to allow at full flow the velocity of the flow to push any settled particles back there. Here's an example of one of those sets of guidance based on the inside diameter of the drain and what is the roughness of the drain, what kind of minimum recommended grade to allow for flushing out of material. Okay. So I'm going to stop this video here, and I'm going to make a second one that's got the example problem of doing one of these things all the way through.